I would like to call here my friends from Lyondell Basell, Roberto Marisaldi and Marco Bassetto. Just a few words about Roberto. He's been in Lyondell Basell for more than 26 years, and he's been with us for a while now, so he is not a client, he's a friend of ours. And he's been an administrator of Seeq platform for over a year, whereas Marco Bassetto is an engineer in charge of pilot plant changes. So I'll leave you the floor. Good morning, everyone. Thank you, Matic and Seeq, for inviting us. We are Lyondell Basell. Just a few words about the company for those who don't know us. We are a company that's going through a huge sustainability revolution like all chemical industry companies. And despite that, we are among the main leaders of polyolefin manufacturers in Europe. We have 20,000 employees distributed between the United States and Europe and a small percentage in South America and Asia. Where can you find our products in your daily life? Pretty much everywhere. In cars, both inside and outside. In food products for food safety and access. Caps, closures that you find on bottles, for example, or yogurt packagings. Healthcare, so hand sanitizers, biohazard bags, pill coatings, renewable energy tools and parts of machinery. So pretty much everywhere. And where are we? We have more than 100 manufacturing sites all over the world, with more than 50 tons of global capacity. We work in Ferrara, the main site in Italy. And in Ferrara, where we work, we have one of the main research centers. Let's switch to our use case, which was started from the need to have a predictive machine for hazard situations. Marco is going to explain you later how the server works. We used our data structure. We are very old PI clients. And after BI, we have a server. And data are collected from different sources, from a PC server in our case. And above AF servers, we also have a couple of servers, Seeq server and a data lab server. And that's because our data are confidential. So we need to have our data infrastructure safe. At the top to the right, we have an AF example with more than 30,000 elements synchronized and more than 3 million elements. This project lasted years, and we're going to tell you about it in our use case. So we imported into our elements size, length, whatever is related to rating, and other data, which have a symbol, a label. So for each equipment, we can see how the equipment was built and the behavior. This allowed us to import data very easily. We imported some data from PI, but most of the data were imported towards AF, which is way more comfortable to do. so that with Seeq and its workbench, we could work on them. Now I'm going to leave the floor to Mark, who's going to tell you more about how we did it. Thank you, Roberto, for your introduction and for this overview about the data architecture. My name is Marco Bassetto, and I deal with pilot plants and labs. This use case that we are going to present is a case of reliability of the off-gas treatment compressor. This compressor, receives off-gas from pilot plants. It compresses them from an initial pressure to a final pressure, and then sends them to a distillation center. When this compressor switches off unexpectedly, the off-gas must be sent to torch instead of treatment. So if this happens, we lose that fraction of polyolefin because we have blends of raw material, so that's a cost. And we also lose thermal energy. So, if we switch to the use case, the compressor, the off-gas compressor, stopped 5 times last summer. And this is why the goal of our use case was to create a model that could identify the input variables of the compressor, thus predicting future stops. The project was completed following these steps. So first we identify the model input variables in Data Lab for the compressor status. So basically we obtained the machine learning inputs, and then we switched to the training phase of the model based on a supervised algorithm consisting in a random forest classifier that will identify operational conditions that might compromise the compressor functioning. And after the validation of the model, we implemented it. The model can be deployed both offline to identify the root cause of failures in Workbench, but it can also be deployed online with a dashboard that helps operators preventing failures real time and also monitoring the machine status and also making decisions in case it is necessary. So let's switch to a more detailed description of our model inputs. We select variables of the model. As you can see, you might think that operators work on the plant daily, and so it is easy to identify root causes of an arrest. But actually, as Roberto said, we work in a research center, so we work with pilot plants, which are conceived to be flexible, of course. However, there can be many variables, such as composition, temperature, and other types of variations, which is why sometimes it is not only one deviation or one signal that can be easily identified with the workbench, causing the compressor's failure, but also a combination of multiple factors. So we adopted a hybrid approach. As you can see in this slide, we started from around 140 events and failures. We launched a Python screen in Data Lab, which identified and removed the variables that didn't contain useful information, and we also try to identify at first the process dynamic to understand the most impacting variables on the compressor. As you can see, the outcome of this script is a list of signals that have a score based on their importance. So we chose as model inputs the first 15 signals, and we also added some more signal based on our practical plant experience, which is why I defined this approach hybrid. We matched the machine learning with our own experience. So once we identify the variables, we switched to the training phase of the model. These are the results. The model was obtained by launching a Q-search analysis from Seeq. And as you can see, the first red signal is the absorption of the compressor, so how much energy it consumes. Every vertical signal corresponds to a non-consumption of energy. In the middle, in the blue thread, you can see the probability calculated by the model, so the likelihood of having a compressor shutdown. So you can basically predict it and organize the activation of an alarm after a certain threshold, which can help operators and warn them that we are in a critical situation. Here, there are some capsules that represent time frames where the alarm would have been active before the actual compressor shut down. And to the right, you can see the duration, the anticipation that the model would have warned for a possible shutdown. The model was then validated against unseen data with the application of Q-search, thus training the algorithm. You can see here December and the pattern of the likelihood of failure before the actual shutdown. So this proved that the model was reliable and we could proceed to the other phase of implementation. A few slides ago, we showed you a blue trend that represented the likelihood of a shutdown of the compressor. This trend can actually be divided into sub-trends that represent the contribution of each variable used as model input for the compressor shutdown, the likelihood of shutdown. Of course, this could look confusing, adding 15 or 25 other inputs. So it is more convenient to keep the trend view for the global likelihood of a shutdown and using the monitoring of each variable. So the color represents the intensity of a variable and how it is contributing to increasing the risk. And of course, the red variables represent the most critical situations, the variables that are mostly impacting in increasing the likelihood of a shutdown. So the model can be used both offline, generating these maps in a context of past failures, to identify quickly the red variables, so the ones that cause the shutdown. And then once you have identified these variables, you can take a further step analyzing the trends. So here, for example, we have in the orange line the gas flow, and in blue the ethylene flow, whereas below you can see in blue the likelihood, the global likelihood of a shutdown, of a failure, and in purple and green the contribution of the two variables that we represented in the middle. In this case, it seems that the compressor shutdown was caused since there was a likelihood that increases with the increase of the reactions, the compressor might have shut down for a lighter composition of off gases together with fluctuations of the global flow. As I was saying before, the model can also be used online through this dashboard that you can see. So on the left, we have an indicator that represents the global failure, and you can monitor the well-being of a machine real time, and if something happens, this indicator goes towards the red zone, thus quickly identifying the variables that are putting the machine into danger. So after this deployment, we switched to a fine-tuning of the model using some ideas that we could use in the future. So for the fine-tuning, basically, the model was improved and can still be improved, tuning the model parameters by trial and error. And every time a new failure occurs, hopefully it never occurs, but when it does, the model can be updated each and every time, adding the new data to the model training set. And regarding future projects, we want to use this approach with machine learning to also improve other equipment reliabilities, for example, for the refrigeration cycle packages. And we also want to scale up this solution that we identified in the R&D center in other production plants with all the consequences. I'm going to leave the floor to Roberto for some final comments. So, a summary of our use case. We wanted something that could improve our compressor's reliability, so we selected our algorithm and we implemented our model, obtaining some results. So just an introduction before talking about positive consequences. We said that the operators couldn't understand why a compressor would shut down, so we gave our machine learning algorithm some information. But last summer, it stopped 5 times. So basically, operators were busy doing other things, and they cannot just spend all day checking the machine. We believe that being able to create predictive machines can really be the way towards a faster and easier implementation of machine learning in production. So reliability ensures a recovery of C3 contained in the off gases, saving up to 6,000 euros for each shutdown. With shutdowns, we usually waste not only money but also energy and raw materials and thermal energy in general. And we lose around 600 to 1,000 euros per hour with that type of energy loss. If we're not able to recover them somehow, it means just burning them, turning on the torch, and more CO2 emissions. And also doing something that's criticized by public opinion, which means emitting more CO2. So our final goal is scalability. So we want to really encourage a scale-up of this solution to other manufacturing plants, showing people that we can really extend this idea to other compressors in the world. We're talking about dozens of thousands of cars and machines, and we really hope we can make this solution more popular. Thank you. These are our names and contacts if you want to contact us.